All right, welcome to Math 150, Section 1, Lecture 20, give or take. What I want to do today is I want to take advantage of the fact that we have a flipped classroom, where you've been watching some of the videos, and this gives me a little bit of time to do some material you wouldn't normally see in a first course. You don't need more than what you've already done to understand and to see it. I'm actually going to give you a lecture that I would give in my Math 341, Stat 341 probability class. The prerequisites for that class is just multivariable calculus and linear algebra. If you are truly interested in probability, the linear algebra can often be waived. It's more for mathematical maturity, for experience dealing with things, because the class is more proof intense, but you don't need real analysis, and you don't really need that many of the methods from linear algebra. You just need to be comfortable with a more proof environment. We've talked about that there are two ways to integrate in multivariable calculus. What are our two tricks? Yes?
Change your variables.
Change your variables. And the other one? What's the other major technique we have for multivariable calculus? Yes? Reversing order of integration. I'm going to teach you a third method today. This is the advanced method. It's integrating without integrating. So I'm going to show you how to get certain integrals without doing any integration by using some basic facts about probability distributions. So we say x is a random variable. Just making sure I'm in focus. Maybe not entirely in focus. So we'll say x is a random variable with density f of x. So I'm putting the subscript x to remind ourselves that the density is coming from the random variable x if the following is true. F of x at any point x is greater than or equal to 0. The integral from minus infinity to infinity of f of x dx equals 1. So something happens. You never have negative probabilities. We would say the probability that x takes on a value in an interval ab would just be integrating my density from a to b. And then we'll let big fx of x be the probability that x is at most little x. And this would be the integral from minus infinity to x of the density, and I'll use t as a dummy variable, dt, because I'm using x as my upper bound of integration. So it's the probability I take on a value no larger than little x. Well, by the fundamental theorem of calculus, the derivative of this is just my density function. So they often call big F the CDF, the cumulative distribution function, and we often call little f of x the PDF, the probability density function. What I want to do today is I want to give you a sense of why are we spending so much time proving these results in multivariable calculus? What is this used for? This will be an introduction to probability. It will be an introduction to statistics. One of the other classes you can go to after this is Stat 201. Hopefully you are aware that course registration for the spring is coming up soon, and it's time to start thinking about courses. I want you to have a sense of, do I want to go to linear? Do I want to go to stats? Do I want to go maybe eventually to probability? What can I do with the math that I'm learning? All right, so what I want to do now is I want to talk about a specific probability distribution. So I want to talk about the chi-squared distribution. And to do the chi-squared distribution, I first need to introduce a very nice function. It's called the gamma function. And it's defined as gamma of little s is the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx, at least if the real part of s is greater than 0. We've seen this function before. In an ideal world, we would have several days and we would explore it very slowly. There is no homework for Monday. There's only an optional homework assignment. So it's out of 0 points. Right, and I think there's only 2 problems. I'm not positive. I'll have to check. What I'm going to do is I'm going to give you a list of statements that you can improve about the functions today. And so in the interest of time, I'm not going to do all the calculations. You don't need to do them for this class, but if you want to try to get a sense of, are you ready for these next classes, here are some things to try. You can treat them almost as practice test problems. So the first thing is, whenever you see an integral like this, you always want to ask, does it exist? Is the integral well defined? Is it finite? Well, the first thing is the function is non-negative. So if it exists, it's not going to be because positive and negative parts are canceling. It exists only if the decay is sufficient. As x gets very, very, very large, we have exponential growth, exponential decay, but only polynomial growth. So think of s as 2018. So for very large values of x, we have x to the 2017 over here, and we have e to the negative x. Exponential grows far, far faster than a polynomial. So a 1 over an exponential decays far, far faster than a polynomial, and this will converge. If you want, we've seen the Taylor series of e to the x is greater than or equal to x to the s plus 8. Let's not use 8. Let's use 9 over. Let's take s equals 2018. E to the x is greater than or equal to x to the 2020 over 2020 factorial. And the reason this is true is I'm just taking one term in the Taylor series expansion. So since I'm only taking one term and it's positive, this is going to be greater. So what this means is 2020 factorial over x to the 2020 is less than or equal to e to the negative x. I'm sorry, is greater than or equal to. So now if I multiply by x to the 2017, we see that this is still greater than that. Well, this is just 2020 factorial over x squared. And that's greater than or equal to e to the negative x, x to the 2017. As x gets very, very large, this is integrable. 1 over x squared, the antiderivative of this is 1 over x. Okay, if I'm evaluating at 0, I have a problem. But if I'm integrating from 1 to infinity, this is finite. So because this is finite, I know this integral is well behaved at infinity. Where else do I have to make sure it's well behaved?
At 0.
I have to make sure it's well behaved at 0. Okay? So is everybody okay with the argument that it's well behaved at infinity? Now we just need to look at what's going on near 0. So near 0, well, e to the minus x. So before, we were looking for an upper bound for this. What's the largest e to the minus x is going to be if x is near 0?
Can you repeat the question?
Sure. How large can e to the negative x be when x is near 0?
1.
Yeah, if x equals 0, it's 1. So we know e to the negative x is less equal to 1. So e to the negative x, x to the s minus 1, is less equal to x to the s minus 1. So if I integrate this from 0 to 1, it's less equal to the integral of this from 0 to 1. So when will x to the s minus 1 be integrable? As long as the exponent here is greater than negative 1. If it is negative 0.9, then when I integrate it, I get x to the 0.1. And then when I evaluate it in 1 and 0, it'll be fine. If s equals 0, I would have 1 over x. When I integrate that, what's the integral of 1 over x? Natural log. So I would get natural log of x, and that would blow up. The natural log of 0 is negative infinity. So this is finite if the real part of s is greater than 0. If you want, you can just think of s as a real number, but it also makes sense if the real part of s is greater than 0 and s is complex. Okay? So this function is well defined for all these values of s. So this makes sense. Okay? We've talked a little bit about where you've seen this before. Here's a great application. So I'll do properties. The first is that gamma of s plus 1 is s times gamma of s. And this is often called the functional equation. And I'm going to leave this as an exercise. The proof is integration by parts. So you have to figure out what is u, what is dv. Right? So that's a really good exercise. A consequence is if you do the calculation, gamma of 1 is 1. Gamma of 2 is 1. So by induction, every value is 1. What do you think? All right, let's do a few more. Gamma of 3 is 2. Oh, it's the Fibonacci numbers. Right, so right now, there's still too many possibilities for the pattern. Let me do another one. Gamma of 4 is 6. Gamma of 5 is 24. Any thoughts on the pattern now? So does anybody recognize these numbers? 1, 1, 2, 6, 24.
Yeah, I mean, it's factorial.
Yeah. 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. If you look, basically, gamma of n plus 1 is n factorial. We have talked about how mathematicians often have annoying conventions. The way the gamma function is defined, it's gamma of n plus 1 that's n factorial, not gamma of n that's n factorial. If you could define things, what would you want gamma of n to be?
N factorial.
You'd want it to be n factorial. So this means one of two things. Mathematicians just don't care about you, and we made a mistake. Or, and this is the one that's true, there's actually another place where the gamma function appears or comes from, and in that situation, this is the better normalization. And that's actually what's going on. In the other setting, this is really the best way to define things. Not surprisingly, there is a function closely related to the gamma function, which just shifts the argument by 1. So if you know that gamma of s plus 1 is s gamma of s, well, if we just use that, then we get gamma of n plus 1 is n gamma of n. By induction, gamma of n is just n minus 1 factorial, so you get n times n minus 1 factorial, or n factorial. So if you can prove this functional equation, then you get gamma of n plus 1 is n factorial, when n is a positive integer. It turns out you can define the gamma function at places other than integers. And one of the most important ones is gamma of a half is the square root of pi. This leads to one of the most absurd things you will ever see in a math class. If I interpret this correctly like this, gamma of a half, well, that's the same as gamma of negative 1 plus 1, right? Does everyone agree that negative 1 half, so negative 1 half plus 1 is a half? So this really should equal negative 1 half factorial. Can somebody give me an interpretation of 3 factorial or 4 factorial?
Yeah, it's every single integer, 4, 3, or 4.
Well, that's how you calculate it. Can you give me what does like 3 factorial represent? You know, it's 3 times 2 times 1, but can you give me what that might represent? Don't try it.
Like if you're picking like out of like a group.
So if you have 3 people,
Yeah.
it's the number of ways to order 3 people. You have 3 choices for who's first. Once you've chosen who's first, you have 2 people left over for who's second. You multiply, and then you have 1 person left for third. So 3 factorial is the number of ways to order 3 people when ordering matters. So if sometime in your life you have negative half of a person, and you want to know how many ways can I order negative half of a person, the answer is the square root of pi. What this means is that this is no longer the same as the factorial. This is a function that interpolates, that generalizes the factorial function. At the positive integers, it's the same. At these other places, you've actually seen something like this in the past. When we did the geometric series, 1 plus x squared plus x cubed plus dot 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 equals 1 over 1 minus x. This makes sense only if the absolute value of x is less than 1, but this makes sense for all values of x other than 1. And I'll just write if the absolute value of x is less than 1. All right. The way you can actually see this is you can look at, we proved this in class, the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 dx equals 1. This is the density of the standard normal. So, density of standard normal. Okay? And so you need to show that this is somehow the same as gamma of a half. And so the proof is let u equal x squared, calculate du, do your change of variables, and this is a really nice exercise to show that this then becomes gamma of a half times various things. And so since it then has to equal 1, you can then solve for gamma of a half. All right. This is the fast blitzkrieg introduction to properties of the gamma function. Okay. Right now it's not clear really why we care so much about this, but these are very useful properties. Okay. So now continuing, I'll try to keep the probability definitions on the board. I want to introduce a new function, a new density, that's going to be related to the gamma function. And this density is going to have a lot of remarkable properties. One of the reasons I like this lecture is it allows me to review a lot of things you've seen. So, try to keep gamma of s is the integral of 0 to infinity, e to the negative x, x to the s minus 1 dx. We say x has a chi-squared distribution with new degrees of freedom. Chi-square with new degrees of freedom if the density function is equal to 1 over 2, actually I think I'm using k in my notes. K halves gamma, I think it's k halves as well. Do you want to make sure it's not a plus 1? Yes, it's k halves. Good. K halves e to the negative x over 2, x to the k halves minus 1. Right? So this is my density for a chi-squared random variable. Okay? So I claim that this is a density. What two things must be true if it's a density? So for something to be a probability density, I need two things to be true. What are the two things?
Needs to be greater than 0.
Needs to be greater than or equal to 0. This is clearly non-negative. Good. And what's the other one? So what's my other property for being a probability distribution?
The integral.
It has to integrate to 1. So as an exercise, you have to show that this integrates to 1. You can see this looks a lot like a gamma function. The difference is I have an x over 2. Here I have only an x. So to show integrates to 1, let u equal x over 2. And when you do this, after you do some algebra, you get that it integrates to 1. So there's a lot of Calc 1 that's going on that I'm just not going to do on the board. You should make sure you can do these integrals. I'm going to leave you with hints, but you should be comfortable doing these change of variables. Okay? Now there's a lot of remarkable facts about the chi-squared distribution. So here's a beautiful theorem. If xi is a chi-squared random variable with ki degrees of freedom, and they're all independent, then if I add them, x1 plus xn that's going to be a chi-squared random variable with k1 plus kn degrees of freedom. So a sum of independent chi-squared random variables is a chi-squared random variable, and the number of parameters, the key factor, is just the sum. So I want to show you how you prove this. To use this, we need the following facts. If x and y are independent, and z is x plus y, then the density of z at some point z is equal to the density of x convolved with the density of y at that point z. And what the convolved means is it means a very interesting integral. It means integrate from negative infinity to infinity of the density of x at the point x, and then the density of y at the point z minus x dx. So again, in a probability class, we'd go through this slower. This is the warp speed introduction. I want you to see where things go. Let's see if this is reasonable. This is supposed to be a density function. What two properties must a density function have? Greater than or equal to 0,
Converge to 1.
and it integrates to 1.
Right.
We're getting faster on this now. So if the functions are positive, their integral is always going to be positive. You have to show that the integral is well defined. I'm not going to bother doing that. I'm going to only just roughly sketch why this is true. Imagine I have x plus y and I want it to equal a value. Somebody give me a number. 3. Excellent choice. So if I want 3, I could have 1 plus 2. I could have 1.5 plus 1.5. I could have 0.2 plus 2.8. I could have lots of different ways of getting 3. So if I want to calculate what's the density of 3, I look at all the choices for x, and this is the probability I chose that value of x. And then I multiply by the probability that y has the corresponding value, and then I just integrate over all things. So this is a little bit fast. There's longer ways of deriving this and more rigorous ways. Is this enough detail? That this seems reasonable, that this should be the density. I'm looking at all the pairs of x and y, and this is the probability of getting both. You can begin to see now functions of several variables. I want to show that this integrates to 1. So let's look at the integral from minus infinity to infinity of fz of z dz. This will be the integral from minus infinity to infinity, and I'm going to write z goes from negative infinity to infinity. The integral x goes from minus infinity to infinity, fx of x, fy of z minus x, dx dz. I need to do this double integral. Any thoughts as to how I should do the double integral? What can we do to evaluate this double integral? What are our two techniques? Yes?
Change the order.
We could change the order. If I change the order, I would integrate with respect to z first. And so if I change order, I have x goes from minus infinity to infinity. This has no z dependence, so I can pull this out. And then I have the integral z goes from minus infinity to infinity, fy of z minus x dz dx. Well, if you look at this, as z goes from minus infinity to infinity, z minus x goes from minus infinity to infinity. So if you let just u be z minus x, this becomes the integral u goes from minus infinity to infinity of fy of u du. What would the integral of fy of u du be from negative infinity to infinity? Yes?
1.
It's just 1. It's a probability function. So this integral will be 1. And now I'm left with integrating the probability density function of x. And what will that be? 1. So that proves that this really is a density. It's non-negative. It integrates to 1. So what we want to do now is we want to prove our theorem. We've actually got a theorem today. If we have a sum of independent chi-squared random variables, then their sum is a chi-squared random variable where the degrees of freedom is the sum. So I claim it's enough to do it for just 2. And the reason it's enough to do it for 2 is the following, is we can do it by grouping. And so we talked about this earlier in the semester. How do you prove the sum rule? Well, in Calc 1, you prove the derivative of a sum is the sum of the derivatives if you only have two terms. What if you have three? Group the first two together and call that your function. So, theorem, proof. So step 1 is grouping. So if you have x1 plus x2 plus x3, you first group this together. And you'll see that this becomes a new variable. Let's call it x12, which is a chi-squared variable with k1 plus k2 degrees of freedom. And then you just bring this one down. And now you're just back in the case of just 2. And then you would have the result for the sum of 3 chi-squared independent random variables if you know it for 2. And now that you know it for 3, now what do you get? What comes next? For 4. We would then just group x1 plus x2 plus x3 and then add x4, and we play it again. So as long as we know the sum of 2 chi-squared random variables is chi-squared with the parameters of the sum, then we have it for all of them. So we just have to prove it for one case. This is where it's going to start getting really interesting, and you're going to begin to see why I want to do this topic. I'm going to introduce integrating without integrating. But as we're going along, you can see we're reviewing a lot of the concepts from the semester. So we're going to now finish the proof. So it's enough to prove the following. Suffices with x1 is chi-squared with k1 degrees of freedom, x2 is chi-squared with k2 degrees of freedom, and I'm going to let ck be 2 to the negative k halves gamma of k halves to the negative 1. That's just the normalization constant in the chi-squared random variable. Rather than writing that every single time, we have a race against the clock today. I need to do this to save a little bit of writing. Okay? So I now want to look at the density. Let's say z is x1 plus x2. So what's the density of z? It's going to be fx1 convolved with fx2 at z. So it's going to be the integral from minus infinity to infinity of the density of the first one at x, and then the density of the second one at z minus x dx. Okay? Now, for my chi-squared random variables, they only are non-zero if x is greater than or equal to 0. So do we agree that for this integration, I don't have to go from minus infinity, I can start at 0? The density function is 0 if the input is negative. So we're all comfortable that I can replace this negative infinity with 0. Okay. But now if you look at this one, once x gets too large, this is going to be a negative input. How large can x be? Z. It can't be larger than z. So I just have to integrate from 0 to z. Let me put everything in. I get ck1, ck2, I can bring that out. Integral from 0 to z, e to the negative input, so input over 2. So I get e to the negative x over 2, and then I get x to the k1 over 2 minus 1. The next one is going to be e to the negative z minus x over 2 times z minus x to the k2 over 2 minus 1 dx. Now you can see why I gave you notes for what I am going to do today. So the notes basically just summarize all these calculations. So if you want, you can just watch what's going on. A lot of cancellation happens. I have e to the negative x halves, and I have a negative x over 2, so they cancel. I have an e to the negative z halves. I can pull that outside the integration, and I get ck1, ck2, e to the negative z over 2, integrate from 0 to z, and now I'm left with x to the k1 over 2 minus 1, z minus x to the k2 over 2 minus 1 dx. Now if I look at this, this integral is nasty. This is not an integral you want to evaluate. Especially if k is an odd number, you've got square roots. Here's the interesting thing. I only care about really the z dependence on this integral, and you'll see why in a moment. So if I look at this, I'm going to change variables. I'm going to let x equal z times u. So then dx is equal to z du. X goes from 0 to z. What's u going to go from? So if x goes from 0 to z, what does u go from?
0 to z over 2.
Not z over 2.
Oh, that's a z there.
That's a z over there. That's why I'm trying to write z's carefully. So what is the largest value of u? 1. So u goes from 0 to 1. This change of variable removes the z dependence in my bound of integration. This term is going to have a z. This is going to be a z minus z. I can pull out a z from this. So when we do the algebra and the dust settles, literally because we're using chalk, we now get it equals ck1, ck2, e to the negative z over 2. Now when I pull out, I'm going to get a z to the k1 over 2 minus 1, a z to the k2 over 2 minus 1. dx is z du. So one of the z's cancel. So I'll get a z to the k1 plus k2 over 2 minus 2 plus 1 is minus 1. You can trust me on the algebra. I checked it last night. And then I'm left with an integral from 0 to 1 of u to the k1 over 2 minus 1, 1 minus u to the k2 over 2 minus 1 du. So all we have to do now is evaluate this integral. This is a terrible, terrible integral. And evaluating this integral is one of the main points of today's lecture. It is to show you that you can actually integrate without integrating. Does this integral have any z dependence? Does it? No, we've removed all the z dependence. What does this function look like here? What does this look like the density of?
The normal distribution?
Not the normal. Normal would be e to the negative x squared, or e to the negative z. So it's not the normal. What random variable does this look like? Well, I've told you. What did I tell you the sum is supposed to be? It's supposed to be a chi-squared random variable with how many degrees of freedom? k1 plus k2. So a chi-squared random variable with k degrees of freedom has function, some constant, e to the negative x over 2, x to the k halves minus 1. What do we have? Well, if you look at what we have some constant, which includes this part, e to the negative z over 2, z to the k1 plus k2 over 2 minus 1. It looks like a probability distribution. So we get ck1, ck2, let's call this integral I k1, k2, has to be the normalization constant for a chi-squared random variable with k1 plus k2 degrees of freedom. We have this has to integrate to 1. The only way this can integrate to 1 is if this is the correct normalization constant. And this is the way to get integrals without integrating. Because I know this has to integrate to 1, the only way it can integrate to 1 is if this thing over here is the correct normalization constant. We now actually know what that integral is. And it turns out that integral is extremely important in probability and statistics. But the key fact is the sum of chi-squared random variables is a chi-squared random variable. Okay. Any questions on what we've done so far? This is a lot. This is the heavy lecture. All right? It's now time to... We're one step away from a very surprising application. I need one more piece of information. I am deliberately not telling you why I care about this. I'm giving you some explanations as to why I'm doing this. This allows me to review a lot of the techniques. We're seeing an application of switching orders of integration. We're seeing connections between areas and probability. We're seeing a little bit about what's going to come in future math classes. But I have a surprising application that you would not expect. And that's why I don't want you to look at the notes right now. So we say x is a normal random variable with mean 0 and variance 1 if the density of x is 1 over square root of 2 pi e to the negative x squared over 2. So this is the standard normal. And the amazing fact is if y is a chi-squared random variable with 1 degree of freedom, I'm sorry, if x is a normal random variable, then x squared is a chi-squared random variable with 1 degree of freedom. So let me quickly show you why this is true. Proof. Let's look at the probability density function for the random variable x squared, the cumulative distribution function. So this is the probability that x squared takes on a value at most little x. This is the same as the probability that negative square root of x is less than or equal to big X is less than or equal to x. This is the same as twice the probability 0 less than or equal to big X less than or equal to square root of x. Okay, so this is going to be twice the integral from 0 to x of 1 over square root of 2 pi, square root of x there, e to the negative t squared over 2 dt. And this is the same as twice the cumulative distribution function of x at square root of x minus the cumulative distribution function at 0. I'm just looking at the antiderivative of the density of the Gaussian. And this was an extra credit problem. If I now want to find the density of x squared, I just take the derivative, and I'll get 2. Well, constant, its derivative is 0. The derivative of this is just going to be little f at square root of x. And then I need to take the derivative of square root of x, which is just 1/2 x to the minus 1/2. Or if you want, you can take the derivative using the value of the integral. So I will leave this as an exercise to show that this is now the density of a chi-squared. You just have to substitute in, but now you can say, hey, I'm evaluating this at square root of x. I'm squaring it. They'll give me like an e to the negative x over 2. It's going to match up with the chi-squared. Okay? So there's a lot of integration problems for you to do and just check things. But the integration we're learning can be used for stuff that matters. All right, we are almost there. All right, so we know that x squared has a chi-squared distribution with 1 degree of freedom. So now let's imagine we add a bunch of normal random variables. So now say xi is normal 0, 1, and they're all independent. Then x1 squared plus xn squared is going to be a chi-squared random variable. If each one of them has 1 degree of freedom, how many degrees of freedom does the whole sum have? N. So we know its density. So the density is going to be, Cn e to the negative x halves, although you'll see later why I want to use the letter r halves, r to the n over 2 minus 1. So that's its density. Okay? I'm going to calculate the density another way now. Okay? So again, a lot of information today. So I'm going to calculate the density another way now. Okay? So again, a lot of information today. it's the sum of independent chi-squared, so their sum is a chi-squared with n degrees of freedom. There's another way to calculate this. Let's let z be x1 squared plus xn squared. What is your first thought when you see something like this? Sums of squares. What should you be thinking when you see a sum of squares? What coordinate system should you be thinking? All right, we'll wait a second. So let's look at fz of r. This is the probability that z is at most little r. This is the probability that x1 squared plus xn squared is at most little r. What is the geometric shape? Yes?
Sphere.
Sphere. What coordinate system should you be thinking of? But now it's not spherical coordinates in 3 dimensions. It's spherical coordinates in n dimension. So we're going to do a change of variables with spherical coordinates in n dimensions. How many of you enjoy spherical coordinates in 3 dimensions? Yeah, they're useful, but... So now we're going to have to write down the angles, find the ranges of the angles, find out what the Jacobian is. So we'll have to do an n-dimensional determinant. Or we can do a backdoor trick and bypass all of this. And we're going to do the backdoor trick. We're not only going to evaluate this, but we're going to get something beautiful along the way. So this is the same as the integral over x1 squared plus xn squared less than or equal to r. Now I have to put in the density. Well, the density of each Gaussian is 1 over square root of 2 pi e to the negative x squared over 2. So I get 2 pi to the negative n halves e to the negative x1 squared plus xn squared over 2 dx1 to dxn. Okay? Now we need to generalize the spherical coordinate transformation. And I claim the following is true. dx1 to dxn is going to be rho to what power? How many rows should I have? Yes?
Is it n divided by 3?
Not n divided by 3. Because we're going to have one radius, and then we're going to have n minus 1 angles. Each angle needs a row to make it a length. It's going to be rho to the n minus 1. Then I'm going to have some nasty function of my angles, phi1 to phi n minus 1. Then it'll be d rho, d phi1, d phi n. So I'm going to get an integral. Rho goes from 0 to r. I'll get 2 pi to the negative n halves e to the negative rho squared over 2 rho to the n minus 1 d rho. And then I'll have the angle integrals g of phi1 to phi n minus 1 d phi1 to d phi n minus 1. I'm not writing down what this is. But this integral has no angular dependence. If I integrate this, what I basically am able to do is, on the surface of these n-dimensional spheres, the function is constant. So another way to look at this is, it's going to be the area of the n-dimensional sphere, and that will give you, that'll be the rho to the n minus 1. If I have a sphere of radius r, its volume is 4/3 pi r cubed, the surface area is 4 pi r squared. This over here is just going to give us the surface area of the unit sphere in n dimensions. And the rho to the n minus 1 would give us the surface area of the sphere of radius. So let's just call that an minus 1. Okay? So this is giving us the probability that we take a value at most r. So the way we get the density is we take the derivative of this with respect to r. This is The cumulative distribution function, that's the integral, that's probability from minus infinity all the way up to r. So the probability density is just the derivative of this. So I now take the derivative of this, and that essentially means I just evaluate this function at r. Or if you want to do it the long way, you have the antiderivative of this at r minus the antiderivative at 0. The derivative of the antiderivative at 0, that's a constant, that's 0. You get the derivative of the antiderivative. These relations invert each other. And so you get that the density, little fz of r, is going to be 2 pi to the negative n halves a n minus 1, the surface area of the n-dimensional sphere, times e to the negative r over 2. Oh, I'm sorry. What's the radius? So I just dropped something, so I'll have to fix that in just 1 second. And then we'll have a r to the n over 2. So I need a square root of r. I made one small slight drop. Let me just quickly see where I am fixing this. Okay, so this is a sphere. What's the radius of this sphere?
Square root of r.
Square root of r. So the radius is the square root of r. So when I have my bounds for rho, how large does rho go up to? Square root of r. So that means it's just a little bit more involved because now I have to use the chain rule again. And so I just have to use the chain rule, so I would get the antiderivative at the square root of r. And so when I take the derivative, I'll get the derivative at the square root of r, and then I have to take the derivative of the square root of r, which will give me an extra 1/2 r to the minus 1/2. And so when I put this in over here, that's why I have an r over 2, because I'm now evaluating this at the square root of r. I'll have a I'll have a square root of r, so I'll have an n minus 1 over 2, but then I have to multiply by the 1/2 r to the minus 1/2, and that will give me an r to the n minus 1 over 2, and I get this extra factor of 2. Or maybe it's 1/2 coming from that. Okay? And so now that I have this, I calculated the density by using generalized spherical coordinates, but I also know the density is a chi-squared. So the normalization constants must be the same. What is Cn? Cn is equal to 2 to the negative n halves gamma n halves inverse. That has to be 1/2 2 pi to the negative n halves an minus 1. So you get an minus 1 is going to be 2. Now I have the 2 pi to the n halves coming over. The 2 to the negative n halves cancels that. I'll have 2 pi to the n halves over gamma of n halves. So we'll just double check and make sure I have not made any errors. Good. And so this is the surface area of the n-dimensional sphere. If I want to get the volume, I now just integrate this against rho, or against r to the n minus 1. So then volume is going to just be the integral rho goes from 0 to r, if I want the n-dimensional volume, of the surface area times rho to the n minus 1 d rho. So you'd get an minus 1 over n r to the n. So you would get 2 times pi to the n halves over n gamma of n halves. If I multiply by 1/2 over 1/2, I have n halves down here. And then if I use my functional equation for the gamma function, this just becomes gamma of the n halves plus 1. So we end in slightly less than 50 minutes with formulas for the volume and surface area of the n-dimensional sphere. We saw a massive new technique, integrating without integration. We used the fact that these must integrate to 1. So there was an enormous amount of information today. This is meant to really give you a sense of where all this material goes and review what we've done. There is a lot here to really understand it. If you want to, go and do a lot of the other calculations. Okay.